Welcome to this deep dive into the OEIS, the Online Encyclopedia of Integer Sequences. It's really an indispensable tool for number theory students.
Absolutely essential.
Today, we're going to zoom in on one sequence, A000201. Our plan is to really get under the hood, see what defines it, and explore some of the connections it has.
Sounds good. A000201, it starts with its recurrence relation. It might look familiar, actually.
Whoa, how so?
It's an1 plus an2, 2. See? Almost Fibonacci.
Right, but with that minus 2.
Exactly. And the starting terms are specific. A0 is 4 and A1 is 3.
Okay, 4, 3. So the sequence goes 4, 3, 5, 6, 9, 13, 20, 31, and so on. I see the list here, quite a few terms.
Yes, it grows fairly quickly. And historically, you might find it listed as M28396 or N0953 in older references.
Interesting historical note, but let's focus on that recurrence. an1 plus an2, 2. You said it's almost Fibonacci. What's the real impact of subtracting that 2 each time?
Well, that's the crucial part. It seems small, but it fundamentally changes the nature of this sequence, even though it keeps a link to that whole Fibonacci family.
How does it change it?
One of the most insightful ways to see the difference comes from combinatorics. Vladimir Shevelov provided an interpretation.
Okay, what's the interpretation?
For n greater than or equal to 3, an is actually the count, the number of n by n matrices that contain only zeros and ones.
So 0, 1 matrices.
Right, but not just any 0, 1 matrices. They have to satisfy a condition. A is less than or equal to P inverse plus I plus P.
Whoa, okay, let's break that down. I is the identity matrix, obviously. What's P?
P is the incidence matrix of the cycle, 1, 2, 3, n. Think of it as the permutation matrix for a simple n cycle.
Okay, so P maps 1 to 2, 2 to 3, n back to 1. And P inverse maps things the other way.
Exactly. So the condition A plus I plus P means the ones in our matrix A can only appear on the main diagonal from I, the superdiagonal wrapping around from P, or the subdiagonal wrapping around from P inverse.
So only on 3 specific diagonals, essentially.
Basically, yes. But there's one more constraint, a really important one.
Which is?
Every row and every column in these matrices must have exactly 2 ones.
Ah, exactly 2 ones. So we're counting these highly structured binary matrices with fixed row and column sums constrained to specific diagonals related to a cycle.
Precisely. And the number of ways to do this for an n by n matrix turns out to be AANN, following that recurrence we started with.
That's quite a connection. Does thinking about it this way combinatorially tell us more than just the recurrence?
Oh, absolutely. It gives the sequence a concrete meaning, connecting it to arrangement problems.
Yeah.
And it leads to another fascinating link.
Go on.
The number of these matrices, AN, is also equal to the permanent of the matrix, I plus P2.
Permanent, not determinate.
Correct. Permanent, it's also equal to the permanent of P1 plus I plus P, which makes sense given the condition on A.
Okay, remind us quickly, permanent versus determinate.
Well, you calculate it using a similar formula involving permutations, like the Leibniz formula for determinants, but you ignore the signs of the permutations. All terms are added.
Ah, so no alternating signs.
Right. And that small difference makes permanence, in general, much harder to compute than determinants.
Yeah.
It connects A000211 to computationally complex problems in combinatorics.
Wow. From a simple-looking recurrence to counting matrices to permanence, that's quite a journey.
Right.
Now, you mentioned the Fibonacci family earlier. Does A000201 have a cleaner link to other famous sequences? I think I saw Lucas numbers mentioned.
Yes, very much so. The relationship to Lucas numbers, which are sequence A00000032 in the OEIS, is incredibly simple.
How simple?
It's just A0ln plus 2.
ln plus 2, where ln is the nth Lucas number. So L02, L1, L2, 3, L3, 4.
Yep, that's the one. So A00 was 2 plus 2 plus 2 was 4, and A1 plus 2 was 1 plus 2, 3. It matches perfectly.
That's neat. A very direct connection. What about Fibonacci numbers themselves? Fn.
There's a connection there, too. Slightly less direct, perhaps, but still elegant. It's AN, Fn plus 1 plus Fn plus 1 plus 2.
Fn1 plus Fm plus 1 plus 2. That's interesting. We know Fn1 plus Fn plus 1 is actually equal to Ln, the nth Lucas number.
Exactly. So it's just another way of stating the same relationship, AN, Ln plus 2. But seeing it phrased with Fibonacci numbers highlights that connection, too. That consistent plus 2 suggests something fundamental linking them.
Okay, so strong ties to Lucas and Fibonacci. What about from an analytical perspective, generating functions?
Yes, the OEIS lists those two. The ordinary generating function, the GF, is given as 21x plus 2x, 1x by 2.
That looks like 2 parts.
It is. You can combine them over a common denominator. If you do the algebra, you get 4 by 2 divided by x1 by 2 plus by 1.
That denominator. by 2 plus by 1. That's related to the Fibonacci generating functions denominator, isn't it? Just with signs flipped.
Precisely. The 1 by 2 is the key part for Fibonacci type sequences. And the x1 factor handles, well, basically the constant offset.
I see. And there's a note about Simon Plouffe.
Ah, yes. In his PhD work, he apparently conjectured a slightly different generating function. It produces the sequence correctly, except for the very first term, R0.
So close, but not quite right for R0. Shows how tricky these can be.
It does. And there's also an exponential generating function, EGF.
What does that look like?
It's 2 plus cosh squared 5 by 2.
Okay, involving exponentials and hyperbolic cosine. That looks a bit more complex. Does it offer different insights?
Exponential generating functions often tie into problems with labeled objects in combinatorics. While the matrix interpretation we discussed isn't directly about labeling, the form itself, with the square root of 5, again strongly hints at the underlying golden ratio connection inherent in Fibonacci and Lucas numbers.
Makes sense. The OEIS page is packed with references, too. For anyone wanting to dig even deeper, could you maybe highlight a couple?
Sure, you've got classics like Riordan's books on combinatorial analysis, foundational stuff. Then there are Sloane's own handbook and the encyclopedia with Plouffe, naturally.
The essential OEIS texts.
Right. For more advanced theory, Stanley's enumerative combinatorics is listed. And crucially, there are papers specifically on permanence of these cyclic Nuon matrices by people like Metropolis, Stein, and also Mink.
So papers directly related to that permanent connection.
Exactly. Plus Plouffe's thesis for the generating function details, and even a paper by Yamamoto related to Latin rectangles, putting it in a broader context. Lots to explore.
And for those who like to compute things themselves, code snippet.
Oh, yeah. The OEIS usually provides those. For A000201, you'll find examples in Maple, Mathematica, Haskell, PRGP.
Yeah.
Pretty useful if you want to generate terms or experiment.
Very practical. Lastly, the cross-references. I see 000220 mentioned.
Right. A000204. That's essentially the Lucas numbers starting LAO, L1, L2, so 21347.
Ah, so it's directly referencing the Lucas numbers ln, which we already established are related by an plus 2.
Exactly. The cross-references just make that connection explicit within the OEIF web. Following those links is often how you stumble upon really interesting patterns and relationships.
So let's try to wrap this up. We started with A000211 defined by AN plus AN22 with a 04A13. And we found it's not just a numerical curiosity, it counts specific 0-1 matrices with 2 ones per row column tied to cycle structure.
Which, remarkably, connects to the permanent of related matrices.
And it has these clean, elegant relationships. AN, LN plus 2, the nth Lucas number plus 2, which is also N1 plus Fn plus 1 plus 2.
Plus, it has characteristic ordinary and exponential generating functions that echo its Fibonacci-Lucas roots.
It really is a great example of how interconnected things are in mathematics, isn't it? Linear recurrences, combinatorics, matrix theory, generating functions, all bundled up in this one sequence.
It truly is. It shows how much richness can be hidden behind a relatively simple definition.
And it really drives home that point about the megas too. Just changing that one constant from the Fibonacci recurrence opens up this whole different combinatorial world and shifts its relationship to the base sequences.
Absolutely. You should now have a much better feel for how these sequences aren't just lists. They're, well, reflections of deeper mathematical structures.
We definitely encourage you, the listener, to check out the A00201 page on the OEIS, follow those references, click on the cross-references, see where it takes you.
That exploration is really where the fun begins.
And maybe leave you with this thought. We saw AN, AON plus 2. The sequence LN, NACTIV2, A00204 shifted also has combinatorial interpretations. How do the constraints in the combinatorial problems differ between a sequence and its shifted version like this? What does adding or subtracting a constant do at the combinatorial level? Something to ponder. Thanks for joining us.